Today we also discuss calculus. Previous class we also give a short video which discuss about just operator, definition of operator, linear operator and example of two operator. We're now going to example of another operator. We'll not check about that this one satisfies this definition or not. This one is too easy, but we not don't that means don't do that, okay? But if you interested in anyone interested candidate is here, they also checked, okay? They also checked by their own effort, okay? If also I do one times this problem, this one is linear operator or not, we check it. Let X norm be an inner product space and let A belongs to X. Define Tx to R by Tx equal to inner product of X A for all X belongs to X. Then T be a linear operator. T be a linear operator or not. First we check what T be additive. T be additive or not. T be additive or not. How we check it? We check it in this way. Let X y belongs to here X, then T of X plus Y equal to what? X plus Y A. Then this one X A plus Y A. Then this one equal to how much? This one equal to Tx, this one equal to Ty. For all X Y belongs to X. Then T be additive. So we write here T additive. Okay. Next we check about if T is homogeneous or not. Then alpha belongs to K, alpha not equal to 0, we are scalar. Then T of alpha X equal to, there is alpha X here A, okay? Then this one happened alpha X A, this one equal to alpha Tx, then this one satisfies T homogeneous. Then T additive and T homogeneous, this implies that T be a linear operator, or gives this conclusion part. So T be a linear operator. We check every problem, every example, but we will not do this, okay? Here we will not do this. We just give some example of linear operator, okay? This one is an example of linear operator. We now erase this portion and also going to another discussion of, okay, another discussion we also going to now. X equal to Rn, X equal to Rn and A belongs to X, A equal to A1 A2 an, okay? Then define T Rn to R by Tx equal to Xa, then Xa inner product equal to summation Ai Xi I equal to 1 to n. Then TVA linear operator, okay? We also check it this one is linear or not. Again there was some problem. Also check it this one is linear or not, okay? Then we next discuss about that. Which portions we also discuss? We also discuss some non-linear operator. That means we write here T X Y Z. It is this portion, non-linear operator. How this one non-linear operator or construct Tx equal to x square, Tx to x defined by this one. Then Tx plus y equal to x plus y whole square, and tx equal to x square, ty equal to y square. Then tx plus y does not equal to tx plus ty. So tv not additive. Then tv not linear. Okay. Understand tv not linear. Then next we going to another non-linear operator. Here write txyz equal to axby plus cz square. Here y. This one we an online non-linear operator. We also check it. Okay, if t is linear. And another important topics, if t be linear, then t0 equal to 0. Okay, and also we're going to another example. We erase this portion and going to another example. Here we write x equal to c to the power n, y equal to c to the power m. Then a equal to aij m cross n, or n cross m. Here be a complex matrix, okay. Then what happened? If t x to y by tx equal to ax. Okay, then this one we check it. This one be linear or not. Okay, tx plus y equal to ax plus y, ax y additive, this happened. Then t of alpha x equal to a alpha x. Okay, then obviously alpha is common, and so this one is be a linear operator. So t be a linear operator. Okay, we also check it. Next we also discuss another operator. That means here we write norm x equal to x whole to the power half equal to square root of inner product of x. Obviously this one equal to square root of summation I equal to 1 to n xi square greater than equal to 0 for all x belongs to Rn. Okay, then norm x equal to 0 implies x equal to 0, and norm of lambda x equal to mod of lambda norm of x. Okay, and norm of x plus y less than equal to norm of x plus norm of y. These conditions are hold for any norm. Okay, also write this one here. Then we also going to another definition. This one is boundedness of an operator. Okay, we are also going to definition of another one. Here we write boundedness. Let xy be linear space. Let xy be linear spaces, and where x equal to Rn and y equal to Rm, and t x to y be a linear operator. the operator T is said to be bounded, then the operator T is said to be bounded if there exists k greater than 0 such that norm of Tx less than equal to k norm of x. Okay, for all x belongs to x. Then we call this operator be bounded. Okay, then operator, when one operator is bounded, this one is an example. Now we talk about zero operator. Okay, zero operator. Zero operator is also bounded. When zero operator is bounded, 0 equal to norm of 0 less than equal to k norm of x. Okay, for all x belongs to x. Again, identity operator is bounded. Okay, then not 1 equal to 1 norm of x. Okay, equal to norm of x. Then any linear operator is always bounded. Then any linear operator Trn to Rm is always bounded. Okay, then this one we write here CAV, all continuous functions if AV to R or C, any one is right here. That means which are continuous. Then this one obviously one space. Okay, again we write this one is linear space or not. CAV of a linear space. CAV be a linear space. Okay, now we also going to this derivative. Okay, we erase this portion and going to derivative, definition of derivative. We erase that portion. Here we write derivative. Let C be a non-empty subset of R. Let C be a non-empty subset of R with interior of C not equal to 5. Let if C to R be a function and P belongs to interior of C then F is said to be differentiable. Okay, at the point P, at the point P, if limit x tending to P, fx difference Fp divided by x difference P exists. This equal to LP derivative of f at point P. Okay. Then we talk about here f is differentiable on C. F is differentiable on C. F is differentiable on C if f is differentiable for all points of interior C. If f is differentiable for all points of interior C, that is L3 exists for all P belongs to interior of C. F is differentiable on C if f is differentiable for all points of interior C, that is LP exists for all P belongs to interior C. Okay, then define f dash x equal to Lx where f dash x equal to interior of C to R such that f dash x is called the derivative. F dash x is called the derivative of f. Okay, that means here define f dash x equal to Lx where f dash x equal to interior of C to R such that f dash x is called the derivative of f. Now thus f dash c equal to limit x tending to C fx difference fc by x difference equal to, this implies that limit x tending to C here fx difference fc by x difference C difference f dash C equal to 0. Okay, then we erase our portion and going to discussion about that. This equal to 0. This implies limit x tending to C fx difference fc difference ax minus c by x minus c equal to 0 since a equal to f dash c. Okay, so ax equal to f dash cx Okay, now also gives definition of derivative. Next we talk about directional derivative. Okay, we also gives definition of derivative in R. We also then their domain is R. Now we talk about directional derivative. Okay, so we erase this portion and going to discussion about that. Here we write directional derivatives. Okay, let C be a non-empty subset of Rn. Let C be a non-empty subset of Rn. With interior of C not equal to phi. With interior of C not equal to phi. Let C belongs to interior of C and U belongs to Rn. Since C belongs to interior of C, then there exists an open wall. VRC, some ball around C for some r greater than 0, such that VRC subset of interior of C. Okay, let C be a non-empty subset of Rn with interior of C not equal to phi. Let C belongs to interior of C and U belongs to Rn. Since C belongs to interior of C, then there exists an open ball PRC for some r greater than 0 such that PRC subset of interior of C. Let F C subset of Rn to R be a function. Note that if U equal to 0, then C plus DU equal to C belongs to BRC. Okay, for all T belongs to R. Further, if U not equal to 0, then C plus DU belongs to BRC. Okay, if norm of TU less than R, this implies T less than R divided by mod U, since U not equal to 0. Then the directional derivative of F at C, then the directional derivative of F at the point C in the direction of U, is denoted and defined by we is a portion defined by DUFC equal to f dash cu equal to limit t tending to 0 f of c plus t of difference f of c by t. Okay, provided the limit exists. Provided the limit exists. Okay, then we also talk about this one is the directional derivative at the point C in the direction of u. Okay, directional derivative of f. Now we also going to one example. Okay, we write here examples. We are also going to some examples of directional derivative. Okay, then first define if r square to r by f of xy equal to x square y square. Then find dxy f of ab. Then f dash avxy equal to limit t tending to 0 f of av txy difference f of av by t. Okay, then what happened here equal to limit t tending to 0 a plus tx whole square b plus ty whole square difference a square b square by t. This equal to what? This equal to limit t tending to 0 a square plus 2atx plus t square x square plus t square x square and b square plus 2bty plus t square y square different square b square by t. Okay, then what happened? Then we also is a portion and going to forward discussion of that. Okay, then this one equal to limit t tending to 0 here t multiplied by 2 square by plus 2ab square x divided by t here r of t square. Okay, we'll not calculate this one. Then we show that 2a square by plus 2ab square x, this one is the limit of this. So what we write here, we also write that thus the directional derivatives exist for any point at all for AB, for point AB at all direction. Thus the directional derivative exists for for AB in all directions. Okay, so now we also discuss another example, which one is a famous example. We write here and write f of xy equal to xy divided by x square plus y square, where xy not equal to 0 0 and 0 if xy equal to 0. Then we have to show that directional derivative is exist or not. That means we checked it. We checked f dash 0 0 xy equal to limit t tending to 0 f of 0 0 plus txy difference f of 0 0 divided by t. Then what happened? We erase our portion and going to this conclusion of that. This one equal to limit t tending to 0 f of tx dy difference f of 0 0 divided by t, limit t tending to 0 tx dy divided by square root of t square x square t square y square difference 0 by t. So this one equal to limit t tending to 0 here xy by square root of x square plus y square. Okay, this one is the result. Then what happened? Then we also see that any direction, that means dxy here f of 0 0 equal to xy by x square plus y square exists. Okay, now we talk about if in 0 0 direction, then what happened. Okay, if we talk about here c, then limit t tending to 0 here f of c plus t 0 difference f of c divided by t. Then what happened? Then this one equal to f of c difference f of c equal to 0. So in 0 0 direction this one is 0, and if xy is not equal to 0 0, then this one is exists. So directional derivative also exists in this direction. Okay, now we also going another example. Okay, another example. Now we erase this portion and going to another example. We write here number 3 f of xy equal to x square y divided by square root of x square plus y square xy not equal to 0 0 and 0 if xy equal to 0 0. Then t xy f of 0 0 equal to limit t tending to 0 f of 0 0 txy difference f of 0 0 by t equal to limit t tending to 0, here t square x square y divided multiplied by ty divided by t. Okay, then this one equal to limit t tending to 0, here t square x square y. Okay, sorry, divided by, here divided by t square x square plus t square y square. Okay, then this divided by, here t square root of x square y square equal to limit t tending to 0, here t x square y divided by x square y square. Then this one equal to what? 0, because in our portion t is given. So directional derivative exists, okay, in any direction at the point 0 0 directional derivative is exist. Now we're going to some observations about that. Okay, we're going to some observations. These observations what tell us? We write here observation. First we talk about d xy f00 exist in all direction, okay, and then we also talk about we define also fxy equal to something xy by x square y square, that means another if xy equal to here xy by x square plus y square. Okay, xy not equal to 0 0 and 0 if xy equal to 0 0. Okay, then what happened here? dxy f of 0 0 equal to, we write limit t tending to 0, here f of dx dy difference f of 0 0 divided by t equal to what we get? We get limit t tending to 0, here t square xy by t cube x square y square. Okay, this implies that limit t tending to 0 xy by t x square y square does not exist. Okay, so their directional derivative does not exist for this function. Then we also if x equal to 0 or y equal to 0, that means if the direction have x equal to 0 or y equal to 0, then this one is exist. Then d of xy f of 0 0 exist. Okay, if xy not equal to 0, then this one is not exist. Xy not equal to 0 0, if this one happen, then dxy f of 0 0 does not exist. Okay, then we also going to another portion we also write here. We erase that portion and going to another discussion of that. Okay, we write here, suppose if C to R be a function or functional, okay, such that the directional derivative exists. Directional derivatives exist. Directional derivative exists at C along U. Then DUFC exists for all U belongs to Rn. Okay. Then DUFC equal to f of u is a mapping from Rn to R. Okay. Then here some condition, C subset of Rn and interior of C not equal to phi, then this one happen. Okay, and this one linear or not, we don't know, which may be linear or non-linear. Okay, then we also give some figure. Here Rn, here C, then we here some point U. Okay, then this one is R, just real line, and DUFC, this one DUFC. Okay, and obviously if U is another R, then this one is some, that means give some value. Okay, so directional derivative obviously gives some value. Okay, then today we stop here.